So hello, everybody. Welcome to yet another installation of our astrophysics seminar. It's a great pleasure to have with us today Erika Florio. Erika did her undergraduate studies at Kenyon College in the United States, where she majored in physics, minored in mathematics and Spanish. So she likes to visit. She's now a PhD student at the University of Cambridge in the UK. And she's here on an extended one semester, I think more or less, yes, visit under the GAPSTI program, which also makes connections between Cambridge and institutions in Greece. And we're delighted to have her talk to us today about what she's doing actually in Cambridge. Here we're doing a little bit of turnaround together, but in Cambridge she's working on gravitational waves from the inflationary vacuum. So without any further ado, Erika, the floor is yours.
Excellent. Thank you so much for that introduction. Yes, so if I haven't met any of you before, I am Erika. I will be talking about my PhD work. As always, if you have any questions about what I'll present, do raise your hand at any point. I'll stop for questions at various points, but also feel free to raise your hand. Right, so the thing that I do at Cambridge is I make relativistic simulations of gravitational waves during inflation. So I am going to hopefully start the talk. Do this? Yeah, we can do that. Amazing. So I'll start the talk by just giving a brief outline of inflation and highlighting the sort of key features that I'm going to talk about with that. And then talk about how the primordial gravitational wave background that comes from inflation is really interesting for studying inflation itself. Then I'll give a really brief overview of numerical relativity, where we solve GR on a computer, and then present the results from my most recent paper, which you can find here if you want to scan up to you. This is a validation study of our example of our numerical relativity code, and it sort of tells the world that we were able to reproduce linear theory, and we can go ahead and start doing some more nonlinear physics. And then finally, I'll end with a few words on where we're going to take the project next. All right. So inflation, as I'm sure many of you know, is a theory of the early universe where we have this period of exponential spatial expansion. And it happened really early in our universe's history. So we know that what inflation was probably comes from some theory of high energy physics. Now, it turns out there are a lot of options from high energy physics as for what inflation actually could have been. This is a list taken from a paper from way back in 2016, showing just a subset of the possible inflation models that are out there. And this list would be bad enough if I hadn't left out the fact that there was another half. And there are actually significantly more models than we really have time to understand and study. And sort of the upshot of this is that the data sets that we use to constrain inflationary theories, these sort of observations of the CMB and large scale structure, we don't have enough data yet in order to really cut down these models to only a couple of key candidates. Now, that being said, we can, of course, do constraints. So this paper back in 2016 used the Planck map to cut down about a third of these theories. They became disfavored, but 2/3 of them still remain. Recently, a team doing baryonic acoustic oscillation measurements also combined their results with the Planck data in order to rule out a lot more models. Unfortunately, this mainly resulted in them excluding this phi squared model, which, as you will see later in the talk, is actually our simplest and most well understood model of inflation. So this is telling us that inflation perhaps is a lot more interesting than we perhaps thought it might have been before we started doing this precision cosmology stuff. Now, a lot of these constraints are coming from observations of the CMB. We're looking at these scalar perturbations, the structure that forms in the early and late universe. But scalar is not the only method by which we can study inflation. We can also presumably study it using gravitational waves. So I'm sure many of you have seen plots similar to this and talks about gravitational waves. You have this big spectrum where physics at different scales can produce gravitational waves at different frequencies. So we have these, from these super high frequency gravitational waves produced by supernova all the way up to these massive, supermassive black holes merging at the centers of galaxies and producing these really long gravitational waves. But as you can see from this middle band, the gravitational waves coming from the early universe, or particularly inflation, can live anywhere along the spectrum. We're really not very well constrained. But this is a good sign for me as a theorist, because that means that as we continue to improve the sensitivity of all of these different detectors up here, all along the gravitational wave spectrum, then we have a great opportunity to continue constraining inflationary theories through gravitational waves, no matter how good any particular one of these experiments is going to become, because we can live anywhere on the spectrum. Okay, so now just a really brief introduction to make sure everyone's on the same page about inflation and its physics. So inflation is an FLRW spacetime. It is a spacetime that is homogeneous and isotropic, and so it has, on homogeneous scales, the following metric, where it have 1 degree freedom in the gravitational sector being the scale factor. Inflation is defined as a period of time where the scale factor is an exponential function in time. So this is the exponentially expanding thing that we always talk about. And it turns out the easiest way to get this form of the metric is by having your matter being some kind of scalar field. So that's going to be our matter model. If we plug all of this into Einstein's equations, which of course determines the way that gravity and matter work on the largest possible scales, then we can come up with the following set of equations governing the inflationary system. So the first one is an equation of motion for the scale factor. This is the Friedmann equation, and it gives the way that the scale factor changes as a function of the energy density that we have in our universe. The second is called the Klein-Gordon equation, and this is essentially telling us the way that the scalar field is evolving as a function of time. These are both equations of motion. First order, second order, these can be integrated in order to find a particular solution, right? And the last equation is a constraint equation. This just tells us what our energy density is in terms of the kinetic energy of the inflaton field phi and its potential energy. Now, the potential is the key here, because when I talk about different inflationary models, what I mean is that I'm specifying a different functional form for this potential. And this is key because as we change this potential function, we're going to really be able to change the dynamics that we get out of a particular inflationary model. So as a simple example, I'll start with our favorite toy model of inflation being V is 1/2 m squared phi squared. This produces a linear dynamics in the inflaton field phi, because if we plug back into the Klein-Gordon equation, we see that phi double dot depends linearly on phi. There's also this friction term that depends on phi dot, and this is an equation of motion that is actually exactly solvable. We know what the solutions are, we can write them down analytically. They're going to be sinusoids that oscillate with a period related to m, and they're going to be damped due to the presence of this friction term. And although this model is very simple, it gives us a lot of intuition as to what actually happens during inflation. At the beginning, we have our field sitting way high up on its potential somewhere, and it's very slowly rolling down, being damped by this friction term. But as the field starts to reach its minimum, it's going to start oscillating. And as the field oscillates, we get into this period called reheating, which is super interesting. I don't have a ton of time to go into it, but it's thought that this oscillation in the phi field at the end is what produces the particles that then create the hot Big Bang. Super interesting stuff. Ask me about it later. Right, so then if we plot what phi looks like as a function of time, we get our damped sinusoid, the thing that we were expecting just by staring at this equation. All good. System, well understood. However, as you remember from the first slide, this is actually ruled out. So it's not physics. Very sad. But there are still models that aren't ruled out quite yet. One of the more interesting ones for my work is called axion monotony, where we take our toy potential, m squared phi squared, and we add an oscillation on top of it. It produces a shape that looks kind of like this. And what's going to happen with this is if we plug back into the Klein-Gordon equation, just like we did before, we end up with this mass term that is no longer a simple linear function of phi. Right? We have the sine term, and if you Taylor expand the sine, you can pull the phi out, but what you find is that this mass thing, which becomes like an effective mass, is going to be m squared plus something, but the something is time dependent. And when you have a time dependent effective mass, that means that different modes in your inflaton field phi can interact with each other in such a way that they can couple and they can resonate, and they can produce really large perturbations. And this breaks linearity. So whenever you have parametric resonance, that usually means that in order to get the correct physics, you have to go to numerical methods. And so that is what I do in my work. But just to touch on gravitational waves again, before I go into that, this paper, number 4, did a numerical analysis of the axion monodromy model, and they extracted a gravitational wave signal from it. And this is shown here. As you can see, the power spectrum is really cool, right? The spectrum that comes out of axion monodromy has a really interesting shape, and particularly the amplitude is going to change a lot based on the model parameters that we choose. This is the big lambda and the little f here. And so what that means is that for these interesting models of inflation like axion monodromy, they're producing different shapes in the gravitational wave spectrum, which means that gravitational waves are really useful to constraining the parameters of those models. Yeah, question.
Yes. So, I mean, it's axion-like inflation, right? So
yeah.
How is this term related to like the properties of like axions as possibly the particles?
Yeah, so it does come from the quantum field theory description of the axion. In terms of the exact mathematics in order to get down here, it's something that I haven't derived yet, but I do know that when you write down an axion, it's going to end up with a potential that has an oscillation in it, and that's why we call it that, right? We're not saying the inflaton is the axion, but we're sort of giving it these kinds of properties. And this is good when you want to think about theories like supersymmetry, where you have a bunch of fields and they exist at different energy levels. The inflaton could have been an axion-like field at a particular energy. Does that sort of answer your question?
Yeah, you don't have to go too often.
Okay. Oh, thank goodness. I don't know if we have enough chalk, but okay. Right. One more slide, and then we'll get to numerics. Amazing. So I'm actually something called a lattice cosmologist. That's what I do. Lattice cosmology is literally solving the nonlinear matter equations of inflation on a computer. It's a super diverse field. People do a lot of different work in this, and it can sort of be understood as grouping the way that they treat gravity actually in their simulations. So all of these simulations have nonlinear matter equations in motion. Some of them solve on top of a flat background. These simulations tend to focus more on interesting kinds of matter. For instance, this one did a gauge field as the matter model. Some others treat gravity perturbatively. So in these cases, you're going to have a Newtonian potential that is standing in for your gravitational metric, and then you're going to solve these things. And these simulations are really useful for studying late time dynamics. How do your cosmological parameters change when you have some nonlinear scalar field that's doing crazy things? And then I am of the kind of people that solve the full Einstein's equations on a computer, which is really hard, but really useful and necessary, particularly for cases where you're making compact objects. So some models of inflation resonate so much that they create overdensities big enough to produce primordial black holes, and you need NR to do black hole stuff. And so hence we have to do this. But the point being that it's a really diverse field, and everyone who works in it is really cool, and all of their simulations are applicable for different scenarios that you might want to look at. So if you're interested in numerics, there's a lattice cosmology code for you. All right, so now I'll give a brief overview of numerical relativity. Any questions though, before we move on to that? Amazing, cool. So, as you may remember from a course you took on GR, or perhaps you solved GR in your daily life, in which case, amazing, hello. Einstein's equations, G mu nu equals 8 pi T mu nu, this is really code for a second order partial differential equation for the metric in time. And we know how to solve PDEs on a computer. And to do that, we need 4 ingredients. The first is a notion of time, which in GR, as we know, is non-trivial. We need a target function, something that we're evolving as a function of time, we need initial conditions. So that's going to be some specification of our target function on an initial slice. And then we also need our target function's time derivative on that slice, since this is a second order PDE. So once we've got those, we can integrate using something. Newton's method, in my field, we use something called the Runge-Kutta algorithm, which is where we use 4 points in order to do the interpolation, is really common. But the point being that once we have these 4 ingredients, it's all just numerics, which is in itself very complicated, but solvable. Heinous, but solvable. So for this talk, I'm going to just walk through how you find those 4 ingredients in Einstein's equations. And our first thing, of course, is finding a notion of time. So we want to find a notion of time. We have to split up our metric in terms of a time direction and 3 spatial directions. And the way that we do this mathematically is by writing down a metric that looks like this. This is the ADM metric. And here I've introduced 3 new variables. We have the lapse, which is alpha, the shift, which is beta, and gamma ij, which is our spatial metric. Now, alpha and beta are what we call gauge variables, and they control our coordinate system. They're non-dynamical, they're not physical, but they're really useful for ensuring that our simulation remains stable. Alpha sort of intuitively measures the distance in time between 2 different spatial slices, and then beta measures sort of the way that the coordinates move around as you move forward in time. So these are gauge things. And then our physical thing that we want to measure eventually is gamma ij. This is our target function. Now, of course, we also need our target function derivative in time. That is going to be this thing called the extrinsic curvature, Kij. And as you can see, it's basically proportional to the time derivative, gamma ij. This is good. So once you write down these equations, the metric in this form, you can then plug this into Einstein's equations and find the PDEs in terms of these variables. This is called the ADM equations. Sadly, ADM is not well posed. The mathematical definition of this means that if you take some initial data and you want to evolve it forward in time, the forward in time solution does not depend uniquely and continuously on the initial data that you give. Practically, this means that if you try to plug initial data into these equations and evolve forward, your simulation is going to crash. And it's not going to return anything useful. But this is what people were trying to do for many years, for many decades. All we had were the ADM equations, and people tried very hard to evolve them, and they couldn't get it to work. But then, around 2005, B, S, and N came up with this new decomposition of our evolution variables that then created a well-posed system that we could evolve. So in order to make this last decomposition, we are going to split the spatial metric into a size, chi, its determinant, and then a unit determinant metric, chi. Gamma, tilde, there we go. Same thing with k, except this time we define its trace, k, and traceless part, a tilde ij. Then we're going to actually plug this into Einstein's equations and find 4 different equations that independently evolve these variables in time. And that is going to be our new system, the BSSN equations, which are well posed and can actually be integrated. And this is what that looks like. It's complicated. It's a lot of math, but there's good news, particularly for me, because in cosmology, a lot of these terms actually go away. We don't need all of them. You know, when you do a black hole simulation, you do need all of them. But it's still okay because we can see the structure, right? We can see the structure in this equation. The first 2 equations are basically telling us that we have a first time derivative of our target variable, and then we define that as, you know, k for the scalar part, and then a tilde ij for the tensor part. And then the second 2 equations are really fundamentally the equations of motion. They're telling us that the first time derivative of velocity, or second time derivative of our target function, is equal to things that involve the curvature of space-time on a particular spatial slice. This is r and rij. This comes from the Riemann tensor, of course. And also matter, right? So these variables s rho and sij, these are projections of the stress energy tensor on a particular spatial slice. So even though it might look kind of terrible, What we actually really have here is just a function. Double time derivative is matter plus some other stuff. And so that is something that we can evolve for sure. Now, there are a lot of numeric relativity codes out there. Each has different pros and cons, just like with lattice cosmology. The one that I work on is called GR-Chombo, and it is developed and maintained by the GRTL collaboration. It is interesting because it uses a technique called adaptive mesh refinement to evolve these equations. So if I have some computational grid, it's going to be some cube with points in it. And normally the way you might do an evolution on this is that you sort of evolve this cube of points forward in time, and they keep the same spacing with each other. But what AMR does is it says, okay, if I have like a region of high curvature where I need better resolution or to resolve the physics, I'm going to refine my grid locally. And so as you can see here, in regions of high curvature like near a black hole, we get higher refinement, and that means that we are much better at evolving systems that have different length scales, like the binary black hole system, which is really close together, compared to this massive extraction radius that you have to use in order to extract the gravitational wave signal from that binary. Right, this is where it is useful. But GR-Chombo actually is not the end of the story, because the entire world is being eaten by GPUs, apparently. We are now moving GR-Chombo onto a new AMR library that runs on GPUs called AMRX. I'm one of the GR-Techland developers, so if this sounds cool to you, I'm happy to talk about it. But here I'll just show a little animation, a side-by-side comparison, apples-to-apples test between GR-Techland and GR-Chombo. This is showing we get the same result in both codes, but it also shows, right, this adaptive mesh structure around these black holes that's spiraling into each other. We're going to have a lot of cool new features, GR-Techland. Hopefully we can do some cool new physics with it, so do stay tuned. We'll be releasing it publicly at some point, like the next year or two. So anyone can have a look and see how it feels. Right. So now I'm going to get into the results of my paper and my particular example of GR-Chombo, now in GR-Techland. But before I do, any questions about numeric relativity? Great, we're all numeric relativists now in the room. Amazing. Cool. Okay, so the goal of my project, my PhD project, is to put gravitational waves in inflation, evolve them with Einstein's equations, and see if using the fully nonlinear evolution scheme changes them. In order to do that, we need to start by setting our initial conditions, right? Target function, first time derivative on the initial slice. There are a couple of ways to do this. One part of numeric relativity I didn't go into a lot of detail in is called constraints. So we have a set of constraint equations in NR that need to be solved on the initial slice. They essentially tell us that matter and energy are being conserved and that we have a valid solution of Einstein's equations on our first slice. To get initial conditions in NR, you can solve the constraints iteratively, or you can start in some sort of linear regime where you have a known analytic solution and then evolve that forward into the nonlinear regime with your nonlinear evolution scheme. And we chose to do the first one to start out with. Okay, so we're going to start our simulation in a regime where cosmological perturbation theory applies. In CPT, what you do is you take the standard FLRW metric and you allow perturbations in each of the components. So time, space-time, and space-space. We're going to be interested in my project in breaking apart and really finally separating the scalar degrees of freedom from the tensor degrees of freedom. And so we're going to do that decomposition just here now. We all know that vectors have a scalar and vector part inherent in them, so we can do that decomposition easily. Turns out tensors have 2 scalar degrees of freedom, 1 vector, and 1 tensor degree of freedom, where Eij is transverse and traceless now. So this is our gravitational wave. So we're also going to ignore vectors. Now why? We love vectors. They're just as much of a part of the party as anything else. But it turns out that during inflation, vector perturbations decay. And they just kind of continue decaying for like generically during inflation. They're not going to be present. And so since we're starting in the middle of inflation, vectors, not relevant for our dynamics. So then we plug this back into the metric, we get our full starting metric with 4 scalar degrees of freedom, 1 tensor degree of freedom. And if you initialize the tensor to be transverse traceless and make sure your initialization here is gauge independent, solve the constraints of first order. Done. Initial conditions, done. Now I'm going to spend 2 more slides talking about the initial conditions, so they're not done yet, but this is a good starting place. Now, my PhD thesis is focused on gravitational waves. I have a collaborator, Jan, who's also in my group. His focus is the scalar part. So he took the scalar aspects of this equation and sort of did everything I'm going to do, but with the scalar sector. But for our validation work, we just do tensors. So that means for the purpose of this paper, we actually get the super simple metric, which is just scale factor, gravitational wave. This is what we're going to start out with. Now, in order to get the initial conditions really working, we need to be able to set up our BSSN variables that we evolve in terms of these CPT variables. We do that by comparing to the definition of our BSSN variables, and then we can make the following correspondence where our background lives in chi and k, the background being the scale factor and the parameter. Yeah. And then our perturbations, hij, live only in the metric gamma tilde and a tilde. Now, if you're in the middle of inflation, it turns out the Friedmann equation is a lot simpler to solve. And if you sort of start with a known model of inflation, a known form of V of phi, then you can figure out what H is on your initial slice, no problem. But initializing hij is a little bit more complicated, right? Because we're going to have perturbations in our tensors. And the way that we model fields with perturbations in them in lattice cosmology is we do something called making a semi-classical approximation of a quantum field. And that is a lot of words, but essentially what it means is that we want our field to sort of act a little bit like a quantum field, right? Or in inflation, we have these fundamental fields. They are quantum, particularly below the horizon. And we want to try to model that in some interesting way. We do this by making a random realization, but first we need a power spectrum that comes from our quantum theory. So to find this power spectrum of gravitational waves, the thing that we do is first remember there are 2 independent degrees of freedom in our gravitational wave perturbation. This is the plus and cross polarization. We know this. So if we plug this plus cross decomposition into our equation of motion that we get from doing what's called the tree level dynamics of quantum theory, so the classical dynamics and quantum system, then we get this Klein-Gordon equation, right, in Fourier space. This is very simple. Now the fact that there's an A here is going to be kind of complicated because for generic inflation, we don't know what form this A is going to take, right? But if we make one more assumption, which is that slow roll, we can actually sort of eliminate the A a little bit and actually write down a solution. So what I've done here is that there is a full analytic solution of H in terms of K, our mode, and in terms of time. Here I evaluated on the initial slice where H naught is H on the initial slice, and this is the form that our polarization field has in Fourier space when we start out. Field time derivative. Good. We're almost there. But this is deterministic. So in order to make a semi-classical thing, we need to make it random. And the way that this is done in lattice cosmology is that you have your 3-dimensional Fourier grid, your grid in Fourier space. You run through your 3D grid and you generate random numbers, 2 random numbers at each point. This is going to be a random magnitude and a random phase that you then apply to your power spectrum. Now for tensors, we do this twice because we have 2 independent polarizations. Then we also need to construct our tensor object. So we need to make hij from hs. And we do this because we can cast the polarization basis tensors in some form that is known throughout the grid. And we can construct it. Yes. Then once we have hij, inverse Fourier transform. And then we have our initial conditions. So what this is a box realization X, Y, and Z for one polarization field. And that looks pretty Gaussian random to me. And this is good. This is actually this is what we want. Quantum fluctuations in a classical system. Very good. And this is just the equation form of what I outlined here, right? So these are going to be random fields. These are sort of known. We can calculate them from basis vectors across the grid, construct the whole thing in Fourier space in a Fourier transform. Done. Now you guys know how to make my computer program yourselves. Right. We thought we had the initial conditions, right? We did the whole procedure I just outlined, did this random magnitude draw, random amplitude draw, applied the things. It turns out that if we then look at the way that this initial Fourier mode that we construct evolves in time, we actually don't get the right solution. So again, this is validation work. We are starting our model in simple vanilla inflation. We should be able to match this blue line, which is just the solution of the Klein-Gordon equation that I noted earlier, right? But we found these spurious oscillations if we did the initialization the normal way, as is normally done in these lattice simulations. And so we were like, this is not physics, this is a bug. There's a bug somewhere. So we went back to the drawing board and we stared at this equation for a long time. Now, we really should be recovering this exact equation on the initial slides and not just its power spectrum. Then we realized by staring at it that if you break this into real and imaginary parts, by breaking this into real and imaginary parts, you gather your terms, you get a complex number that has a magnitude matching the power spectrum you're expecting, but that also has a k-dependent phase. A phase that depends on the mode that you're looking at wherever you are in the grid. And if we then, find the functional form of this phase, which we did, we used that to do our initialization, we got the correct thing. So this means we're able to do a full mode by mode reconstruction of the linear solution in our GI trauma simulation, which is what's shown in these red dots. This is the first time that we are aware that anyone in literature has done this. This field is very new. So this is great. It means we can go on and do some physics now. Yeah, go for it.
Thank you. But since you said meet the evolution, let's say,
Yeah.
like a starting point, then why would you move to make all the modes like be what's the word?
Yeah, doing the matching correctly?
Yes.
Yeah, so, well, this is a function of time. Sorry, maybe I didn't specify that. This is a time-dependent plot. So e-folds is the way you measure time. And so, yeah, so we're doing the time evolution. This is us doing the time evolution and saying it's wrong with this initialization and it's right with this one. Is that your answer? Did you have a different question?
But the last question.
Okay, good. Any more questions? Okay, cool. All right, so now we move on to the actual full validation example that we did, which is studying a particular thing in inflation, which is called horizon crossing. So in inflation, there are two scales that are really important. There is the scale of the mode that you're looking at, so it's frequency, and then there's something called the horizon scale. And the horizon is this physical scale set by inflation. When a mode is smaller than the horizon scale, it's oscillating, dynamical, interacting. And when it's larger than the horizon scale, it's damped away and frozen out and it doesn't evolve at all. So we did a simulation of inflation where we start with all of our modes smaller than the horizon. Then as the simulation progresses, the horizon comes in and freezes everything out until the horizon gets to the scale of the grid resolution, and then everything's frozen out and nothing evolves. And this plot just sort of shows that that is what we do, right? So when the horizon mode is smaller than our lowest mode, everything here is sub-horizon. This is the horizon crossing period. So these points in time, again, e-fold is time. Things are going to be freezing out gradually, and then here everything is frozen. Nothing is dynamical. So we ran this in GR-Chombo. We first checked the background. So we can sort of evaluate averages, right? In our box as a function of time, for instance, the Hubble parameter, check it against the Friedmann equation, and it works. Very good. To pretty high accuracy. We were very happy with this. We can also look at the constraint equations. So if you remember the constraints, measure how well your simulation conserves energy and momentum. Generally, So in NR, they're measured by these constraint satisfaction variables that should be 0, but they never are because computers can't actually do that. But generally, you should see that the constraint variables start low, keep getting lower, or stay constant, and just don't grow. If they grow, you have problems. But we found that our constraints actually did start low, and they started as low as we were expecting, right? We didn't solve the constraints to get our initial conditions, and so we're expecting violations at second order. For these simulations, our tensors have a size of about 10 to the minus 5. And as you can see, even for this really crappy grid, this is 64 points per side, really terrible resolution. We still get constraint violation of the order of h squared. Also very promising. Now we move on to validating the perturbative dynamics. So this is how are our perturbations evolving as a function of time in our tensor field. We look at that by looking at the power spectrum. So for the slide I showed a little while ago on our initial conditions and how we sort of found the right phase for them, we were looking at a particular mode as a function of time. This is just showing the whole power spectrum as a function of time, where we start off with this blue power spectrum and then evolve down in time towards this orange one. The solid line here is the solution to the Klein-Gordon equation. That's just linear order dynamics, and the dots are our GR-Techland simulation, or GR-Trumbo simulation in this case. And as you can see, they match really well. This is very good. We can also get some really nice movies. If we then inverse Fourier transform this, we see that the polarization field generally goes from having these really small clumps in this uprising case, and as things freeze out, the clumps stop oscillating and they get larger. And this is reflecting the change in the tilt of this power spectrum, right? So power goes from being distributed relatively into high modes to being distributed relatively into these low modes. And that causes this change of shape that we observe. So now we wanted to move a little bit beyond the linear order dynamics for this first paper, and we did that by calculating the skewness of our polarization fields as a function of time. So if you remember from the initialization, our fields, when they start off, are Gaussian, or sort of Gaussian, right? We are drawing a finite grid of points, and so there's going to be some non-zero skewness. But as we change our random seed, as we change our random draw, the skewness parameters that we should measure should average out to 0, right? And so we can still go and measure the skewness at different random draws. And we get something that looks like this. So the skewness path starts low, distributed around 0, and then as horizon crossing happens, the distribution widens out, and we get this sort of larger variance and super horizon scales. But again, you can see the skewness is still sort of averaging to 0, right? So what we did is we increased the initial amplitude of our perturbations. So this is going from a simulation where we have large background, perturbations are really small, to simulations where the perturbations are starting to become like the order of the background size. And this is sort of naturally where we're going to see nonlinear effects coming up, right? So what we did is we did this increase in amplitude, calculated the skewness function of time, and then noticed that at higher amplitudes, which is shown by these sort of green dots here, we get sort of a larger spread, right, than the lower amplitudes, which are these blue lines here. And so we decided to quantify this by calculating the absolute deviation of the skewness as a function of amplitude averaged over random configurations. And we found that we got a bigger absolute deviation for larger amplitudes. This is telling us that the nonlinearity solely from the fact that we are evolving Einstein's equations is actually present when we are leaving the perturbative regime. Because skewness is one statistical measure that we can make of whether or not a system has been evolved nonlinearly. This comes from particle physics. If you have questions, please ask me.
So
Yes.
from the skewness, you can tell the evolving time.
No, the evolving time is we measure that independently. So this is just
No,
time variable.
I mean, if you were
Yeah.
to see non-Gaussianity in your actual spectrum.
Yeah, the one that you measure on the sky.
Yeah, yeah.
Yeah.
then can you invert that and tell at least the lower limit of inequality times for the inflationary vacuum?
Of like the amplitude, you mean? Yeah, so that's a good question. So yes, you're right. If we measure a bispectrum on the sky, it's going to have some amplitude. That's the skewness. And then the thing is that probably the bispectrum itself is going to give us more information. So its amplitude is going to be more related to the particular inflation model underlying the thing than like the amplitude of the gravitational waves, right? This actually, all these simulations, again, we're done with m squared phi squared, already ruled out. So we would have to redo this simulation with whatever inflationary model fit the bispectrum best in order to get a handle on how much this amplitude of the skewness actually depends on this. And we'd also have to do it with scalars as well, which I'll talk about next. But yes, it's complicated. But this is one part. Right, that will take up that signal. Other questions? Cool. All right, amazing, still a little bit of time. So now I'll give just a really brief overview of where we're going to take the project next. We've got a tensor gravitational wave simulation. It's working well, it's validated, so now we can go on and add other ingredients to it. And the first thing, of course, is scalar perturbations. So like I said, Jan, who is the other member of my group, he has developed a similar pipeline to deal with the scalar parts of the metric. So right now we are combining the two in order to evolve inflation with both scalar and gravitational waves in and see if their interactions are going to produce interesting things in higher order statistics like the skewness, which I was looking for. So what Jan did actually is he created this Python code called stoic_gr, which numerically integrates the Klein-Gordon equation forward to our first slice of GR Chombo. And this allows us actually to start GR Chombo in something that is not the linear regime, like in the middle of an interesting feature. So it creates more generic conditions. What I'm doing right now is taking the spectrum that he gets from stoic_gr and plugging it in and making these random realizations in GR Chombo and seeing what we come up with. And this very first result that we have is very preliminary. We got this like last week. We still need to verify quite a lot of things, but it looks like if we start our simulation with just scalars and no gravitational waves, we see the emergence of a second order gravitational wave background. And this is predicted from linear theory. And if we compare the gravitational waves that we extract from the scalar only simulation compared to what we expect from the simulation where we put first order tensors in, we see that they're kind of close. They're just an order of magnitude off. And for numerics, that's actually not so bad. So we may have actually gotten some physics just by putting these together, which is kind of amazing. We all know that usually doesn't happen. Okay. So once we get the scale, oh yeah, sorry, question.
Oh, okay.
Yeah.
If since now you're trying to cover stuff,
Yeah.
would it make sense to also include now again the vector stuff that you threw out in the beginning, or still no?
Yeah, so the vectors are still going to be subdominant, right?
I mean, the couplings, would they
Yeah, so
do something?
yeah, I'm pretty sure there are some models of inflation that do produce vector perturbations that are non-trivial. It would happen dynamically though.
Yeah.
Yeah, it would have to happen dynamically. So it's entirely possible we need to extract them, right? If they appear, then we'll need to know that they're there to extract them. For now, we're not going to include. Yeah. Cool. So once we have the combined cone working, we're going to look at models like axiom and entropy, which I mentioned earlier. These are actually predicted to create gravitational waves through scalar self-coupling that are really large. And so this is definitely a place where we're going to need to use numerical relativity because we might get really big gravitational wave signals from this. And then that's really going to help us with our final goal of constraining these theories with GR. Okay. So I'll just leave some conclusions up here. Basically, the result of my PhD work so far is that if you can design your numerical simulations really well and do a really good match to perturbation theory, then you can create a tool that's really powerful. And in particular, I'm hopeful that the simulation I've come up with now will be able to let us constrain inflation through precision cosmology, like the skewness parameter that I talked about before. But of course, that can only happen if we see a gravitational wave background. Particularly if we want to compare to the CMB, we're going to have to do a lot of data analysis, like taking all the dust out so we don't try to see gravitational waves and then actually just see dust. And that is where a lot of your guys' work come in. I know there are people here who really care about dust and taking dust out of CMB maps. So, yeah, let's chat. There are a lot of people to reference. I made a lot of references on this slide, so please have a look. A lot of these people are doing really interesting work, but I'll leave it there. If there are any more questions on anything I covered, I'm happy to take them.
Thank you, Erika. Any questions for Erika? Any more questions?
Yes.
Say?
So.
Yeah.
My naive understanding of inflation is that the horizon is fixed and basically things just go out, right? So the way you model the perturbations, is it that you start on horizon scales and then do what?
Yeah, so you're right. So the way that I talked about it before is a little bit not actually what happens. You're right. So the horizon size is fixed. What's happening is that the co-moving length scale is growing.
Okay.
Yeah. So we start off with all of our modes and, you know, our whole computational domain inside of the horizon. What's actually happening is that the computational domain's growing, right? So the largest mode then passes the horizon scale all the way down to the smallest mode, and then the smallest mode eventually passes the horizon scale and everything's frozen. So you're right, we start with things smaller than the horizon scale, and then we evolve them forward.
Right. So
Yeah.
then why do they grow? I don't understand this. Where does quantum mechanics come into place?
Yeah, so quantum mechanics comes into play in the initial conditions only, right? Our evolution scheme's fully classical, but we want to try to like add stochasticity because, right, when the inflaton field, we can talk about the inflaton for a second, when that's sub-horizon, it's quantum. It's a quantum field when it's below the horizon. Now, it turns out you can make a mathematical argument that says as the field modes pass through the horizon, they become classical.
Why?
I imagine what you can do is calculate the commutator and then see that.
There is no observer. How do you make the quantum to classical transition? I don't understand.
Yes.
Why would the wave functions collapse?
Why do they collapse?
Why?
Yeah. I think that question's actually kind of deep because it's right. It's the space-time itself interacting with the fluctuations of the field, right?
Mm-hmm. But
Because-
this happens in all scales, no? Why would the horizon be special?
Well, because on scales much smaller than the horizon, then it's like there's no horizon at all. You're in an approximately Minkowskian space-time. And so quantum mechanics is like totally fine,
I see.
right?
Oh, and then gravity, the gravitational interaction comes into play.
Exactly,
Okay,
and it comes
I
into play
see. I
afterwards.
see. Okay.
And there are people, yeah. And then the gravitational interaction, I imagine decoheres the quantum state. And there's math behind that.
Okay.
Yes.
So it's like,
But presumably gravity is also quantum, right?
Yeah, but we don't see that in this, right? Because we're evolving Einstein's
Yeah,
equations.
so these are, I mean, you assume Einstein.
Yeah.
Okay.
Yeah.
How long is that?
How long do you assume Einstein?
No. How?
Sorry.
But that's the $1,000 question.
Yeah.
Yeah,
Okay.
yeah.
Right.
I mean, the thought is that if you're like at the very beginning of inflation, you know, everything's quantum and you can't really do that much. But we're in the middle of inflation. And so things below the horizon are quantum, things above are classical.
Do you
This is fine.
accept inflation in your simulation?
So we don't yet. We could. I think that'd be interesting to like start in the middle of inflation, then exit. Other people do exit inflation. So there's a ton of lattice work on reheating, which is the thing that happens at the end of inflation. Tons of people do numeric relativity for this. This is where you get primordial black hole formation and compact objects. That's not currently within the scope of our work, but I think it'd be really interesting. And a really good target for gravitational wave signals as well. Yeah.
Other questions? I have more, but.
Yes.
Coming a little bit more from the observational side. So you showed at the very beginning, right, that basically inflation can predict gravitational wave at any kind of frequency.
Yeah.
But we do have already a number of observational constraints, not only from gravitational waves, but also from many other methods that constrain the abundance of primordial black holes.
Yes.
There's a different mass scale. So does that take into account in any kind of way? Like, I mean, your density fluctuations cannot be arbitrarily in amplitude, right? For example, if you cannot produce primordial black holes at a specific mass range because it had been ruled out by, you know, CMB accretion, or many constraints are out there.
Yeah, exactly. In terms of like, how do those constraints impact the kinds of simulations that we could do?
Yeah, like how would you, could you inform your simulations like with some of these observations? Right?
Yeah.
Inform
Yeah.
value.
Yes.
Yeah, exactly. So you're definitely right. The simulations that we're doing in the middle of inflation are happening on scales that are like CMB scales. So there is a degree to which we can't push our perturbations too high, or else we will violate CMB bounds, right? For people who want to do things in reheating, this is more where you get into the primordial black hole abundance bounds, right? It turns out primordial black holes are actually kind of hard to make in numerical relativity, and no one's been able to do it yet. But if we are able to get a primordial black hole out of one of these simulations, then what that allows us to do is then we can measure the abundance in our simulation. And then, right, if you measure the abundance in the simulation, compare that to the abundance bounds that you get from observations, then that allows you to say, model, done, ruled out, not realistic. So that is where that comparison would come in. Yeah, I guess for the end of inflation, it would be more like combining the results of simulations and observations to rule stuff out, rather than setting it up. Does that make sense?
Yes.
Yeah.
Well, like this will part of the initial conditions and like what you can get out of it.
Yeah.
And then
Yeah.
predict.
Yeah, exactly.
So the horizon scale in all this is assumed to be above the Planck scale, right?
Yes.
Well above the Planck.
The smaller ball?
Hmm?
The smaller ball, how does that compare to the Planck scale?
Oh, that's a good question.
Well, you
Sure.
assume classical GR,
Yeah.
so you have to be above, right? All the substrate is
Yeah.
classical,
Exactly,
and
exactly.
that's what allows the coherence.
Yeah.
Otherwise,
You're quantum, and you're just quantum.
yeah.
Exactly. So yeah, the smallest one is also
Yeah,
fine.
sorry.
Yeah, no, go for it, go for it.
Around,
Yeah.
Yeah. Imagine you guys might be getting that.
Yeah. Super interesting. Thank you.
Okay,
Thank you so
again,
much.
Megan.
Thank you for the question.